Welcome everyone to our first bite-sized series webinar. The topic today is FFT fundamentals. First, I'd like to say thanks everyone for joining us today. Hope you find it interesting and everyone learns something. So before we get into the presentation itself, just a little bit of information on myself here. I'm Elliot White, an applications engineer at Prism Sound in the UK. The majority of my role is to work with our customers to ensure that they can reliably and quickly do all the tests that they are looking to perform. So the contents of what we're going to be talking about today, we're going to start off with the time-frequency relationship and why it's useful to understand this. Then we're going to go into the fast Fourier transform itself and the differences between different kinds of Fourier transform. Then we'll move on to the sample window and discuss some of the problems that it can bring for you. Then we'll go on to the window functions and how to choose the correct one for your measurement. Then we'll move on to the picket fence effect and how you can avoid this before finally going on to talk about our smart FFTs a bit. Throughout this session, if you've got any questions, please put them in the questions box because we'll have a question and answer session at the end. So yeah, just anything you thought, just add it in. Okay, so before we start the presentation itself, I'd just like to get a bit of information on yourselves, see how much experience you've got. So I'm just going to ask a question here. I'll just answer honestly because it's all anonymous, so don't worry if you wish you had a bit more experience than you do, because everyone's here to learn things, so don't worry about that. Okay, we'll just wait a little longer and then I'll show the results to everyone. Okay, I'll just close that now and we can see, okay, we've got quite a good spread really. About 16% of you don't really know anything about audio measurement. 31% beginners, and then the majority of you regularly use audio equipment, and then just a small amount of you consider yourselves advanced. Okay, so we'll get into the presentation itself. So we'll start off with a bit of Fourier theory. This says that we can create any continuous waveform by the summation of a group of individual sine waves with varying frequency, amplitude and phase properties. And the number of sine waves this takes would be related to the harmonic complexity of the waveform. And you can see this in the diagram to the left. We've got the individual sine waves, and then below, when you sum them all together, you get that yellow trace at the bottom. Once we know this theory, we can actually flip it around on its head and say that we can deconstruct any wave into its constituent sine waves, and this group of sine waves is known as the Fourier series. This makes the Fourier theory a very powerful tool for signal analysis, because once we've split our signal into its individual sine waves, obviously we can analyse these separately, and it allows us to look at things in a lot more detail. So, okay, the time-frequency relationship. A lot of people will be familiar with seeing a graph similar to what we've got here, where you've got amplitude against time. And similarly, a lot of you will also be familiar with something like an FFT, where you've got a frequency spectrum. But it's less common for people to understand how these two relate to each other, and it's useful to know this. So what I've got here is a little animation. If you had this graph here with your individual sine waves on, and you added a z-axis which you marked as frequency, if you then plot your individual waves according to their frequency, you'd get something similar to this graph here. And if we then rotated our view so that we looked into the frequency axis, you'd get something similar to what we've got on screen now, which, if you're familiar with an FFT, will be fairly familiar, where you've got individual spikes at your specific frequencies. So what we can say is that the time and frequency domains are different perspectives, different ways to look at the same data, and you don't lose information going between the two. It's just a different way of looking at your information. So, okay, why would we want to do this? Well, here I've got a normal sine wave, and I'd like to ask a question for everyone. I want to know, what level do you think that we can visually identify distortion in the time domain? So we've got a couple of answers here: 0.01%, 0.1%, 1%, 5%, and none of the above. Again, this is anonymous, so don't worry if you get it wrong, and if you don't know, just take a guess, and we'll see what people think in a minute. Okay, just wait a little longer, and then I'll bring it to a close, and we'll have a look. Okay then, so let's have a look. What we've got is, again, quite a good spread here. 11% of you saying 0.01%, 11% saying 0.1%. The majority of you have chosen 1%, with quite a few of you picking 5%, and then some of you picking none of the above. Well, the answer actually is none of the above, and we'll see why now if I just take that off. So this sine wave here, if you look at that in the time domain, you can't really see anything wrong with it. But if we actually put this into our analyzer, what we'll see is that we've got almost 5% of distortion there. And if you took an FFT of this, you can quite clearly see there we've got pretty high second harmonic distortion. So the frequency domain allows us to see details that are pretty much impossible to see in the time domain, and that's one of the main reasons why we would want to use the frequency domain. Okay, so what is the Fourier transform? The Fourier transform is a mathematical tool that we use to transform our data between these two domains that I've just been discussing, and you can see the formula for it there. But the Fourier transform itself is actually continuous, so if we want to use our data in any kind of computer or DSP, we have to use what's called the discrete Fourier transform. But this is actually quite inefficient and can take us a long time. So what we use is the fast Fourier transform, which is basically another method of achieving the same thing. It's a much quicker way because it takes out some redundant calculations. So it saves us a lot of time. And we've got a little bit of a practical example of the kind of time differences that it takes between these two methods. The discrete Fourier transform takes n-squared calculations, whilst the FFT only requires n times log n calculations, where n is the number of FFT points we're using. So if we were doing a Fourier transform for what is commonly known as 1k points, it would mean for a DFT you're taking just over 1 million calculations, whereas an FFT takes just over 3,000 calculations. And if we go to the other end of the scale where we've got 250,000 FFT points, the DFT is taking just under 69 billion calculations, whereas the FFT takes about 1.4 million calculations. So you can see there's a pretty big difference in the amount of time it takes to perform these two transforms. Okay, so as I said, Fourier transform is continuous, but it also should be measured over infinite time. Obviously, this isn't really very practical for us, so what we do instead is take a smaller window, which is taken to be representative of the infinite time. But this can bring some complications with it. So I'd just like now to see if people know what complications these are that the sample window can introduce. So just take a minute to answer this question, please. This is a multiple choice, so you can select any that apply. We've got change the frequency of the original input signal, change the amplitude of the original input signal, introduce frequencies not present in the original, and reduce the dynamic range, followed by all of the above. So again, don't worry if you get this one wrong, and if you don't know, just take a guess, because it's good to see what you guys know about this so far. Okay, so I'll just wait a little bit longer and we'll get the answers in and have a look what you guys think. Okay, so we've got quite a small amount of you going for the top two, and then we've got quite a lot of you actually going for introduced frequencies not present in the original signal. a few of you going for reduce the dynamic range, and then the majority of you picking all of the above. Well, the answer here actually is two of them. It's introduce frequencies not present in the original signal and reduce the dynamic range. And they're actually linked by the same cause, really. So we'll go through these now and see why. Okay, so the finite sampling method can lead to discontinuities. And this is because the FFT algorithm that we use actually requires samples both before and after the current sample that we're processing. And this means that if we're processing a sample either near the end or the start of our FFT window, then there's not going to be any data either before or after, depending on where we are, to use, which obviously means that the calculation is not going to work correctly. So what we do to get around this is we effectively repeat the data before and after our actual sample window to simulate having real data there. But this can lead to a discontinuity in the signal if our input stimulus doesn't have an exact number of periods within the window. As you can see here, these red circles, there's a big step in the wave, and that's going to cause a lot of problems. It will basically introduce extra frequencies. Obviously, a big step involves lots of high frequencies, and therefore our dynamic range will be reduced, as you can see in this FFT here. Now, there are two ways we can take care of this problem. Firstly, we can use a window function, and secondly, we can ensure that our signal does have a exact number of periods within the sample window. And I'm going to go through both of these for you. So we'll start off with a window function. A window function is something that we can use to reduce the influence of the starts and ends of the window. You can think of it as a temporal weighting filter, basically. And the result that we get is a product of both the samples and the window function. As you can see here in this diagram, we've got our original wave in green, and then we've got our window function in red. In this case, it's a triangular window function. And the result on the right-hand side, you can see that the amplitude at the start and end is reduced. And what this means is that when we repeat our data before and after our main window, as before, you're not going to get a discontinuity. And the result, if you use an optimized window, is a much better dynamic range. What we've got here is the exact same setup of the two images, but one is using a rectangular window function, which is equivalent basically to having no window function, whereas the one on the right is our optimized Prism 7 window function, which is got a very high dynamic range. And you can clearly see on the right, obviously, those distortion harmonics, which you wouldn't have been able to see at all on the rectangular window. But this improved dynamic range does come at a price. It's a trade-off for spectral leakage. And what I've got here in these two diagrams is exactly the same signal and setup, but I've zoomed in a lot on the actual signal peak itself. And you can see on the left with the rectangular window, we've got a nice sharp peak, but the side skirts come up quite quickly. Whereas on the one with the Prism 7 window, you don't get as much side skirts. You've got a much better dynamic range, but the peak itself is actually a bit rounded over, and it's harder for us to identify exactly what frequency we're looking at. So what is spectral leakage? Well, it's when the energy in the signal leaks out into adjacent bins, and this is caused by our window function. A bin itself is what we call a range of frequencies on our FFT plot that is represented by a point on our plot, sorry. So on this diagram, the left, what you can see, these blue dotted lines are the boundaries between each bin. And you can see this point in the middle of bin 1. That point actually represents that whole range of frequencies. So the balance between the dynamic range and the spectral leakage caused by the window function are actually determined by the shape of the window function. And I'd just like to ask you guys another question here. I want to know, what do you think is the best window function? We've got a couple of choices here: a rectangular, flat top, a Prism 5, Prism 7, and the final one, not enough information to say. So we'll just see what you guys think on this. Again, don't worry if you don't know the answer, because it's completely anonymous and we're not going to be showing anyone up. So we'll just wait a couple more seconds now to get some answers in. And okay, we'll see what people think. So okay, we've got a bit more of a weighted answer on this one. We've got a very small percent of you are saying a rectangular and flat top. About 20% of you choosing the Prism 7, and the majority of you going for not enough information to say. Well, well done everyone. That's the majority of you got the correct answer, because as I said, the balance between spectral leakage and dynamic range depends on the window function, and we may want to prioritize different measurements for different tests that we're doing. We may be more interested in amplitude, we may be more interested in frequency. So the window function you can't tell unless you know exactly what test you're doing. We've got some examples here. On the left I've got a range of window functions, and then on the right you can see their resulting FFT plots. And you can see that on the what looks like a relatively small change on the actual window function itself, it makes quite a big difference to the FFT plot. Okay, so I'd just like to give you guys a practical demonstration of this now with my D-scope. Okay, so what I've got on screen at the minute, up the top left here, I've got a slider here which is changing my frequency of my input signal. I've got a couple of options underneath to choose my FFT parameters, number of points and which window function we're using, and then obviously the main majority of the screen is taken up by our FFT display itself. So what you'll see is, as I move this frequency, the dynamic range does get better as I get towards the middle of this slider here, but it's a very specific frequency where you get an improved dynamic range, and it's very hard for me to manually tune this in. Even if I switch to the fine control, where I'm changing it just by 0.02 Hertz, it's still very hard for me to accurately put this at a frequency where I've got a good dynamic range. If I switch now over to a Prism 7 window, what you'll see is that as I move this slider, the dynamic range doesn't change at all. And this is because of our window function taking care of this discontinuity for us. And again, you can also see, as I was talking about, the peak itself is a little bit rounded off. So it demonstrates the balance between whether you want dynamic range or spectral leakage. Okay, I'll just go back to our presentation now. Okay, so the other method that I talked about, apart from using a window function, was to ensure that your signal has an exact number of cycles within the sample window. And this is known as being bin-centered. Once we've done this, it allows us to use a rectangular window which doesn't introduce any of the spectral leakage. And once we've done this, we can actually do some very unique special measurements, the bin-centered frequency response and a synchronous multitone. So I'd just like to see now how much you guys know about these two techniques, whether you've just heard of them or whether you use them regularly. So this is a multiple choice, tick any that apply, and we'll see how much you guys are aware of these techniques. Okay, I'll just wait a couple seconds more and then we'll take the answers. Okay, so we'll just see what people have said. Okay, so we've got a good spread on this one, really. Almost 40% of you know nothing about these measurements, and then we've got quite an even spread, really, of having heard or having used of these various measurements. So we'll go through now and discuss them, so hopefully everyone can learn something. Okay, so a bin-centered frequency response. It uses a stimulus signal, which, if you listen to it, it sounds quite similar to a noise signal, but it's actually not really random at all. It's a very specific group of thousands of sine waves placed at these bin-centered frequencies. And if you looked at it on an FFT plot with a high number of FFT points, you'd get something similar to this diagram here, where you can see all the individual sine waves themselves. But if we set our number of sine waves to be exactly half the number of FFT points we've got, what you get is a situation where basically it joins up in a kind of join the dots line, and you get something like this, where you've got a frequency response. And the advantages of this method is, well, it's a lot faster and it's a lot higher resolution than what you would usually do in a conventional swept frequency response. In our bin-centered experiment, you would typically, the minimum number of points you'd have is about 1,000 points, whereas it can go all the way up to 256,000 points. And if you think how long it would take you to do a conventional sweep with that many points, you'd be looking at a very long test time. Okay, so the other one, multi-tone testing, it uses a similar technique of very accurately placed sine waves, but this time we don't put one in every single FFT bin. What we do is we make sure, firstly, that all our sine waves are in even numbered bins. And what this means is that we know any distortion components will also be in even numbered bins, because they'll be integer multiples of our fundamentals. So once we know this, we can work out that anything that comes in an odd numbered bin has to be noise. And if we then also offset the frequencies of our sine waves between the channel A and channel B, we can also measure the crosstalk. So a multitone, is a technique that allows us to do lots of different measurements, all from the same FFT capture. So it's very fast and very quick. Okay, so I'll just give you an example of these now. Just wait there while I switch over to my D-scope. Okay, so let me load the bin centers example for you. So what we've got here, at the minute I've just got it joined up. If I take our number of FFT points higher, you'll be able to see the individual sine waves like I showed in the slideshow itself. So now if I switch this over back again to be the right amount of FFT points, you can see our joined up line. And I'll just engage my EQ here, and you can see now how fast it updates, because I'm tweaking this EQ in real time. So the bin center's frequency response is a very good technique if you've got something with any kind of filtering or equalization, where you've got a lot of settings to check on a production line, where you're trying to do it as quick as possible. It's a very good technique to use in that kind of situation. Okay, so I'll just switch over to multitone. Okay, so here I've got a kind of typical setup that you might have using a multitone system. We've got our red FFT trace, where you can see the individual sine waves, and you'll notice that it's a lot less densely packed than our bin centers signal. Also, the trace, we've got a yellow one, which is our frequency response, which is joined up from the individual sine tones, and then we've got other traces which are things like distortion and noise. And you can see we've got our individual numerical readings as well, HF roll-off, LF roll-off, etc. So you can see again, that's a very fast way of doing lots of tests simultaneously. Just go back over to our presentation now. Okay, so another question I'd like to ask you guys now. I want to know, can you read the amplitude of a signal from an FFT plot? So just have a think about this one. We've got a couple of answers. Yes, look at the y-axis. Sometimes only under certain conditions. No, an FFT shows frequency, not amplitude. And I don't know. So yep, a couple more seconds to take people's answers. Again, fully anonymous. Don't worry if you get it wrong. Okay, so let's see what people think on this one. So, okay, we've got the majority of you are going for yes, look at the y-axis. Second highest choice, we've got sometimes only under certain conditions. Only 8% of you going for no, and about 10% of you saying I don't know. Okay, so the correct answer on this one was the second one, sometimes only under certain conditions. And we'll go through why you can't read the amplitude off your FFT now. Okay, so as I previously mentioned, each bin represents a range of frequencies. And this means that if your signal frequency is not at the center of a bin, it's actually going to be represented by several adjacent bins of a lower amplitude. And I don't know how well you can see this animation I've got here, but what it's showing is that when you sweep the frequency, as it passes between the bin boundaries, which here are shown by the red dotted lines, you actually get a situation where your peak looks like it's got the top of it chopped off almost, and if you were to read that, you'd get a lower amplitude. Obviously, I'm zoomed in quite a lot here, so usually when you're zoomed out, you wouldn't actually be able to notice that the top's been chopped off at all. So this means, as I said, you can't accurately read your amplitude directly from the FFT. In this example we've got here, what it's showing is actually you've got almost 4 dB of difference whether you're between bins or at a bin center. So it can actually be quite a large inaccuracy if you're really looking for an accurate amplitude measurement. If you're just getting, say, an eyeball to see if your signal's there, then it's perfectly okay to look at the FFT, but it's not reliable to read your amplitude off it directly. And if you think about this theory, you can actually extend it outwards, that not only would you have to integrate the area under your signal peak, if you wanted to take a noise measurement, you actually have to integrate under the whole range of frequencies that you're interested in. And if you're doing your whole spectrum, say from 20 to 20k, because you're doing a much wider frequency range, the inaccuracy is going to be much higher. So it's not really good to read your noise floor off of directly by looking at an FFT in any situation. So there's a couple of ways that we can actually get around this. Firstly, we could increase the number of FFT points. And what that will do is it'll increase our frequency resolution. So although it doesn't actually reduce the picket fence effect itself, what it does is it reduces the chance of it occurring, as there's more bin-centered frequencies basically, and you've got more chance of being closer to one. But a better way to reduce the picket fence effect is to use a flat top window function, which we'll have a look at now. So what I've got is here in the animation, it's exactly the same input signal, and you can see now that as we sweep the frequency, it stays almost constant at 8 dBu, sorry. But the trade-off for this is a much higher amount of spectral leakage. As you can see, the peak itself is much wider and rounded, and you can't as easily tell exactly what frequency we're at. So I'll just give you guys a demonstration of this now. Okay, so I'll load my picket fence example. So what I've got here is similar to the setup we had in the first demonstration. I've got a slider here which is changing my frequency of my input signal, some FFT parameters down here, and then the majority of our window is taken up by our FFT trace. And these little white crosses I've put on to mark where the bin centers are. And what you see now is as I move the frequency, you'll see the signal move, and it kind of looks a bit chopped off when we're between bins. and you can see it's quite a big difference. And as I said, this is really zoomed in. So if you're on a normal kind of scale for what you'd be looking at your whole spectrum, you wouldn't be able to notice this at all. And so it's very hard to get an accurate measurement by looking just at your amplitude. If I switch this over now to the flat top window, what you see is it's nice and smooth. As I sweep the frequency, it stays at a constant amplitude there. But again, you can see it's a much rounder and fatter peak, and it's very hard for us to accurately say exactly what frequency we're actually at. Okay, so I'll just go back to our presentation then. So another method, the preferred method for us that you can account of both the picket fence effect that I've just been talking about and the spectral leakage that I was discussing earlier, is to use our smart FFT detectors. Now these automatically account for the integration that you have to do, and they'll do this every single time your FFT buffer updates, so you get a quasi real-time reading as well. They compensate for both the effects that I've been describing today, and they'll also do all the maths behind the scenes for you. If you think, we've been talking mainly today about amplitude measurements, but if you're doing a slightly more complex measurement, such as you want to do harmonics ratios or intermodulation distortion or anything like that, then it involves a couple of calculations. And this can be obviously a bit long-winded to do yourself, so it's good because it does all these things behind the scenes for you. Another thing it does, the filters in it will automatically account for any spectral leakage introduced by your window function, and it'll take it. It's aware of how large your FFT is, so it automatically adjusts slightly the filters to account for these effects to give you a repeatable and accurate measurement, which is actually very easy to undertake. I'll just give you a quick example of the kind of things that we can do with a smart FFT. Okay, so what we can see here, I've got loads of different measurements going on at once. I've got second harmonics, individual harmonics all the way up to our sixth harmonic there, total harmonic distortion, noise, amplitude, balance, etc. And I've even got a 50 Hertz mains hum there. So as you can see, this is updating very fast, and these are all nice and easy now. I've not got to do anything, and it's a very reliable way of doing it. And it might look now actually like we've got a pretty busy screen at the minute, but actually we can have up to 40 stereo pairs of these FFT detectors. So what I'm showing you here